Gert would be presenting to us on the resistance fluctuations in contacts under high current loading. A lot of good questions we got on the high current loading. So Gert's area of expertise lies in the characterizing test sockets and interconnects for the ATE industry. Additionally, at GateWave Northern, he optimizes high-speed interfaces and PCB layouts for best performance. Gert has a PhD from University of Wisconsin-Madison. Way to go, Gert. I'm from there too, the master's.
Thank you.
And a diploma degree in electronics from the Technical University of Braunschweig in Germany. He's a member of the Scientific Research Society in Sigma Chi.
Thank you very much, Rahima, for the introduction. And again, good morning, good afternoon, good evening. And to those of you in the middle of the night, a hello from the Midwest. And thank you for coming to this presentation. I appreciate the opportunity to present that here and would like to thank TestConX and the sponsors for that. What I like to do here today is look at resistance fluctuations in contacts when we ramp the current up through the contact. I've done that before in 2009 and looked a lot at the background of this, but today we're going to look at a little bit as to what we can possibly learn here and do with that when we look at a larger number of contacts. So my agenda here is to explore novel ways of assessing current carrying capability and do that through basically through looking at many DC test reports that we've done over the time, and also give you sort of an idea of the feasibility and accuracy of the method. The problem that why are we doing this is that, well, we in testing contacts, we can't always get a probe onto the contact itself or see the contact with an infrared-based thermometer. So typically one assesses current carrying ability by measuring the temperature, but that won't be possible then. And so if we have like contacts that are in the middle of a socket or that are embedded in material like elastomers, for example, it may not be practical to try to measure it with temperature rise. So be nice to have another way to look at it. And the other question is here, we've seen these nonlinearities in contact resistance. Can it be used as a current gauge for maximum current handling in applications, meaning what is the impact for putting a socket that shows some nonlinearities into an application? Here's a quick slide from back in 2009, just to give you an idea of what we're talking about and why we see some of these effects. Perhaps this is not scientific, it's just a sort of an illustration of what we see here. One of the reasons we see effects for high current is that in reality, a contact, of course, is not planar. It has asperities and bumps and valleys, and contact is made only in small areas. So the current density through these areas is much higher than in the rest of the metal, and we can get heating localized in there. And that means we can have shape change and temperature effects, resistance as a function of temperature there. And some of these effects will be reversible, others may not be. The speeds we expect there for these things to happen are probably as quick as microseconds, certainly in the millisecond region. Time constant for an entire contact, for example, is typically less than a second, less than a second and hundreds of milliseconds. Other causes for resistance might be interface layers in form of metal, oxide metal barriers, or so-called Schottky barriers. And of course, those can be affected as well by high currents. They can be even destroyed and so forth. And they're nonlinear. We get essentially then tunneling through an oxide layer in the interface. And that could, in principle, generate gigahertz type noise. And believe me, we've tried to see that, but it's unfortunately not easy. And we have not succeeded yet. There are multiple reasons for that. Number one, the contact resistance, of course, is very low. So we expect very low voltages to exist in these areas. And so the signal levels are low. The other reason is we really don't know at what frequencies that happen. So any any signal that gets generated or any noise gets spread out over a large region of frequency region, so we can't see it. And of course, basically what it really then means is for practical applications, it's also not terribly important. And finally, of course, we can have chemistry effects there. We could have oxidation in the interfaces and so forth, which would be also not reversible. So this is sort of the background why we see nonlinear resistance. So what I'd like to do here now is describe the test environment and how we test quickly, and then look at the collection of large data from tests that we've performed over the years, and look at trends. And we'll do in the process, look at different contact types as well. We'll be forced to do that. So in order to make more sense of the data. The setup's very simple. We place the contact here at the end of the red arrow there to the right of it. We place it between two gold-plated surfaces and connect it to the instrumentation, a current source, and a digital data acquisition system. And we also have a thermocouple that we bring into the area between the ends of the contacts. And generally, we place that in the region where we expect the highest temperature rise. Of course, this may not be the middle as shown here. It may be near the tiny end, near the top or the bottom. But there's only so much one can do with a thermocouple, of course. What we do then is with that setup, we apply incrementally increasing current levels. We go up, for example, by 50 milliamps from step to step. And at each step, we hold for a moment to reach thermal equilibrium. As I mentioned already, that time constants are in the second region. So even with that, it doesn't take terribly long that we don't have to wait for very long to reach thermal equilibrium. And as we measure voltage and current, so forth, we evaluate for resistance as a function of current and compute then the power from that as a function of current also. If we look at such a measurement, an example is shown here. This is not current and voltage. This is temperature rise as a function of temperature of current in a contact. And the temperature goes up and follows basically a square law roughly. Actually, ideally it should. And in this case, we define, in our tests, we often define 20 degrees as a temperature rise that forms the basis for that is the maximum current carrying capability. It is, of course, not the maximum capability that a contact can handle before it gets destroyed. But in practical applications, we may not want to have the temperature rise much in temperature, especially in burn-in or in other high temperature environment tests, because that temperature, of course, goes above the actual already high temperature. So this is just how we do it typically. And if we evaluate for current and voltage, we see on the left side on the graph, the voltage is the dark blue line that rises as current gets increased linearly because V equals R times I. And the resistance stays constant in this particular test, except at the very 0 point, of course, it goes to 0. And it's not the resistance is 0, but we don't have any data there. So there are no irregularities that we can really see. We can compute from those data the power as the voltage times the current, or I squared times R as that is, and that it becomes a square law curve if the resistance is constant. Now, if we derive the change of power as a function of current and plot that, we get a linear slope for a square law curve. We get a linear slope, and guess what? We do see little irregularities here. We have tiny ones around the linear slope here that are from the instrumentation, and then around 6 amps, something a little bit bigger. And so something becomes apparent there, and that is what we're going to focus on. This is, of course, not anything to really worry about here. This is small variation, but that doesn't necessarily stay that way. If we look at the temperature rise or the change in temperature rise as a function of current, we also see this event. We also see a bunch more noise, and that's simply the data acquisition that's granular. So we could, in principle, use the dt of di as well, but it's not as convenient and also potentially not as accurate as the measuring voltage and current.
Gert, sorry,
Yes,
may I ask a question on
absolutely.
the slide that had the dp over di? That is, in all these cases, you're also measuring the power as well as you're measuring the temperature, right?
That is correct. In the instrumentation, well, actually what we measure is the voltage, the current, and the temperature.
And you're calculating the power from the
That is
voltage.
correct. Yes, that's extracted, that's calculated from voltage and current. Okay. So that is a graph here, two graphs from 2009 as well. This is just to demonstrate to you what happens when we have a contact that's not as well behaved as on the previous slides. And this is on SEC 105 compounds that are, of course, more difficult in terms of their interfaces for the real world. And on the left side, we see the same contact first with two successive measurements without any actuation. That's the dark blue and the pink line. And then we'll actuate it and measure it again, and it's the yellow line. We clearly see that when we have when we plot the dPdI, we see that all that changes, and just below 1 amp, actually we get a significant nonlinearity. Then we take that same contact out to 3,500 cycles without cleaning and do 10 successive measurements, and we plot those in a graph with current on the horizontal axis and voltage up dPdI on the vertical axis. And we get this wonderful spikes showing at about 0.5 amp roughly for the 10 successive measurements. And the interesting thing here is, of course, it always happens at the same, basically at the same current. But of course, after that, it isn't always the same. So things change. Not surprisingly, it's a mechanical contact. Anyway, the transition is rather nice, and that's why I've illustrated that here. So we do see irregularities at higher current levels. There's nothing new here. And if we do enhanced processing via the differentiation, we can visualize these. And so from this graph, we can define for this particular contact what we might want to call a low noise limit for applications, namely below 0.5 amps, the contact will be low noise. Why is that important? Well, on the power supply side, it's probably not that important, but it might be on the ground supply side. While these variations are very small, if I have a very sensitive differential amplifier for whatever reason that is used somewhere and I have ground noise, that's not necessarily a good thing, or at least variability. So there may be applications where that is something that we will want to know and to characterize. And can we use this to determine current carrying capability? Well, for that, we have to look at a larger number of contacts. And let's do that here on the left side. I've plotted for the dPdI for more than 70 different contacts. And that, of course, not terribly useful by itself. We see a lot of noise, basically, and squiggles and curves at different slopes because the contacts all have different parameters. So we have to do something to make that more useful for characterization. If we look at the dPdI curves, we find that at low currents, we generally have a linear slope, as it should be, as you may recall from what I said previously, it should be an I squared R behavior, and therefore a linear line in dPdI. So we can determine in the graph, we can put a trend line through it, and then take that trend line and subtract it out of the data. And what we get then on the lower right, you see, we get a line that is basically at zero level up to a threshold when the noise becomes bigger and deviates from that zero level. And as it turns out, that is actually dVdI. It's not dPdI anymore, rather than it corresponds to dVdI. I have set the noise threshold at 2 amps here. That's maybe a little too aggressive, but it just sort of gives you an idea of where we're at. So to show that this is how this compares with delta T of I with the current, with a temperature measurement, here's a graph where we have one of the delta T of I curves in the graph together with the dVdI curves, with 10 of them that were done for 10 successive actuations. And you can see again that the threshold is very pretty well defined here. If we look at where that happens, it's around 1.5 amps. And if we compare that to the temperature rise, we see that happens at about 13 degrees. The temperature is on the right-hand side, the axis. That's about 13 degrees. As you recall, as I said earlier, 20 degrees is what we typically use for characterization of contacts. So 13 is actually lower, so it's even more restrictive. But it's still in the ballpark. So that's encouraging, of course, for if we want to use this for characterization.
So Gert, a quick question on this
Yes.
one is, would you be utilizing a characteristic like this, or could this be a methodology for checking out all performances, especially because you're trying to figure out the current carrying capacity and the delta T? Could this be utilized as a future spec, a methodology for defining a future spec of all the sockets, or the current carrying capacity and the corresponding delta?
Yes, that's a very good question. I appreciate that. Yes, it could probably be done. We will see later for different contact types, we will get different results. And so it could be, I would not want to replace the traditional definition of critical current carrying capability. We'll get to that toward the end. I'm getting a little ahead of it, but it could be an additional specification for a particular contact. Probably shouldn't be taken for just one contact. We'll see that in a moment. But anyway, it could be an additional specification.
Okay.
So that being said, let's take a look at a bunch of contacts. Here are 110 different plus contacts. And we see the Imax as it is defined by the temperature rise, and the Imax or current capability as it defined by, well, I have dPdI, but really it should be dVdI in there. And the horizontal axis is just the contact number. And we see quite a bit of scatter, of course. Ideally, the blue and the pink curved dots should all be on top of each other, but of course, real life isn't like that. If this was a perfect definition of current carrying capability. So in order to see a little bit better what's going on, what I've done is I've taken the dPdI values and subtracted them from the Imax for the dt values. So ideally, we should see 0 if this was giving exactly the same results. It does not, of course, there's quite a bit of scatter, not surprisingly. So it's a mechanical contact. I should like to point out, we look at an Imax that is based on the delta T temperature rise and give one particular value. If we measure 10 different contacts, we get 10 different results. If we measure one contact 10 times, we probably also get 10 different results, just closer grouped together. So the Imax that you find in our test reports is typically a typical value. It is not an absolute value that every contact will have exactly this particular maximum current carrying capability anyway. So we need to keep that in mind. There will always be scatter. That's a subject of a different paper, but anyway.
So a quick question on this is,
yes.
On page 16, you had 3 different contacts. There is no way, with the colors, there's no distinction between the contacts, right? It's all scattered.
That's a good point. Yes, they're all mixed in here. And that's just to confuse the audience. I didn't think of doing it at the time. I'm sorry, but they're all in here. We'll get to that in a moment. What I've done then is I've noticed that at low current levels, we see for one contact type, a lot less variation. So I focused in on that for a moment. And we see here a graph that may be a little confusing. The yellow line, the yellow dots show what it is. It is the Imax, the graph shows the Imax for the 2 different methods of dPdI and the dt as a function of that dt. So we get a linear line that starts at 0 and is exactly linear through the same voltage, same current levels on both axes. So it's the yellow dots. But then we can plot into that the Imax with dPdI, which is the dark blue dots, and the one that one would get for the same contact if we allow 30-degree temperature rise. So that would, of course, be a higher level. And so all the pink dots should be above the yellow dots, which they are. But we see already there's some degree of scatter there as well. And so the upshot of that is here for this type of contact, we see that we get some degree of correlation between the DPDI method and the Imax from the temperature rise, because the blue curves, blue values fall sort of between the 20 and 30 levels. Okay. If we do the same thing for the entire set of data, it doesn't look so nice anymore. So we there get all these various scatterings for different contact types and different measurements throughout. That's just for completion here. So what we've done, well, I'm sorry, I've gotten ahead of myself. The correlation, by the way, for this dPdI to dt is about 0.77, the mathematical value, which isn't terribly good, but it's still encouraging. It's not zero. So it warrants a little bit more investigation, but it is not sufficient to, that goes to your earlier question, should we replace the Imax obtained by the temperature rise with that? The answer to that is no, because there's too much scatter. But if we split this up for 3 different contact types, then we see this is the curve again where we have the Imax and from temperature rise, the blue dots, and that the difference to the one from the dPdI, which is the pink dots. For one, if we classify that by contact types here, we see that actually we do get some better behavior here between the data. The upper left, of course, has by far the most data, so there's more scatter in there. But nevertheless, the dots are grouped pretty nicely around 0, not perfect, but for the second type contact, we see much better correlation really in the lower left corner. That was a one-piece contact, by the way. And on the right side, we see another type of contact, and that, of course, has more scatter again. So if we take into account, if we make ourselves sort of a table or compare what other data we have for a particular contact type, we may get information about the Imax that the contact can handle from the dPdI by measuring only that and not the dt. Brings me to something that we need to do here for calibration. We need to do to calibrate our setup. You may ask, why is that necessary? We have a 4-terminal measurement that shouldn't need calibration. Well, reality is such that it actually does. What we want to do for calibration, we want to bring the contacts together in the test setup together without any test specimen between the two, and then acquire the data for that and do basic post-processing of the data to get rid of any effects of the fixture. When we do that, we see on the left side, we see the brown graph. There's still a pip around 6 amps in here, which shows that even the fixture by itself may not be perfect. But when we calibrate it and take that out, it looks pretty linear. It should, of course, ideally be 0. If I may jump ahead for just a moment, if you look at the left graph here, you see on this one, this wasn't calibrated. You see there's actually, before we reach the threshold, there's already some variation and deviation from 0 in there. You can avoid that by calibrating that out, by doing this measurement. Why do we need to calibrate? There is even the test fixture itself has, of course, interfaces. There may be thermals from that, meaning thermal voltages to dissimilar metals. There may also be, well, different types of materials stacked on top of each other that have different functional behavior when the current gets increased, that sort of thing. So it's a good idea to calibrate. When we do that, we see in this graph on the right-hand side here, we see 1 pogo pin, 5 different pogo pins with 10 times actuation. So it's a total of 50 measurements, 5 different pogo pins of exactly the same type. And guess what? They all do start with their noise at pretty much the same level, at about 1.5 amps here. And so that's very encouraging. So there's some degree of reproducibility here, I would say, that warrants paying attention to this method. And here comes my COVID slide, as I might call that. It's my last one, because quite frankly, I don't exactly know what I was trying to say here anymore. On the left side, we see the DVDI for 10 successive measurements without any actuation of the contact. And you see that there is reproducibility in that there are there's noise happening at similar levels for many of these measurements, but it's not perfect, of course. This was a completely, the setup left in place, nothing changed mechanically, just doing one measurement after the other. We will still have changes as a result of the applied current, because things start to happen when we go into high current limits. On the right-hand side, we see the DVDI for 2 different contact types, each of them with 10 actuations. And this is here just to show you that, yes, with actuation, it changes, but the threshold still is reasonably well defined, in this case, well, for the 2 different types of contacts.
So with the noise threshold on the left, where you did it without actuating the contact, did you allow sufficient time to cool down, or between the measurements, or?
The answer to that is yes, because these measurements, remember, they're a result of taking a curve from 0 amps, gradually ramping up the current in 0.05 amp steps or 50 milliamp steps, going to the maximum current. So we start at 0 again. There's plenty of time for the entire setup to cool back down, and then we start ramping up again. And for each individual measurement in these, as we increase the current, we wait for a specified amount of time to let the temperature settle for the thermocouple to catch up, which of course the thermocouple isn't in here. So, but that we let that settle. But of course, these results might also be affected by the temperature settling. That's a good point, yes. But that should be not an issue here.
Thank you.
And with that being said, it looks like the DPDI, well, I really should say DVDI, is capable of providing stability forecasts for contact applications. And we could even use it for determining maximum current. However, replacing the IMAX definition that we get by temperature rise with that from DPDI does not appear advisable because that's just too much scatter in the measurement. But we can still get a good tool. If we have no other way of doing it, it's better than nothing. So we have to accept that there will be some error, and we can perhaps do bench measurements and compare contacts with different methods, and then compare it to the in situ measurement if we want to do in situ measurements. And well, please keep in mind, if we look at these variations from the DPDI or DVDI, as I mentioned before, the delta T of I current carrying capability definition is also not exactly constant. So we really need to, if we want to use it, we really have to try to make an effort to establish correlation for the particular type of contact. And with that, I should like to thank everyone for your attention and be open to any kind of questions.
All right, so thank you, Mehdi, for asking this question. How will thermal conductivity of pin material length change the current variations?
I'm sorry, I did not quite get that.
How will the thermal conductivity of pin material or length change the current variations? Basically, you're showing the current carrying capacity. And I think the question is, how will the thermal conductivity of the pin material or the length of the pin change the current variations? Basically, another layer of what the dependency could be.
Yeah, the length really should have no impact on that, because the effects that we see here are happening at the contact interfaces. So the length will have an effect on the overall temperature rise, but so the overall temperature rise will be higher and the current carrying capability lower. But the DPDI or DVDI should not be affected by that. As in terms of the material itself, that will have a potentially significant impact on it, and its surface will also have surface roughness and so forth may have an impact on it. I cannot speak to that because we didn't do any investigation of, we did not look with an SEM or so forth. This is work that we did just out of trying to find a way to characterize contacts, not to do a scientific investigation. We don't have any resources to do that. If you would like to commission a study, we'll be happy to do it. So.
Okay. All right. Any other questions for Gert? Going once, going twice? Okay. Gert, I want to thank you very much for this wonderful presentation and all the questions you have heard. And looks like you have a future project on the thermal conductivity. That's a very good question. Maybe that will be next year's paper. But with that, I want to thank you.
Once again, I would like to very much thank our sponsors who have made this event possible with their generosity and have also made it free to attend. Our premier sponsor, Kohu, our emeritus sponsor, Johnstech, our honored sponsors, ISC, iWind, and TSE, and our distinguished sponsors, Backer Hotwatt, Innovative Circuits Engineering, JMT, NIDIC, SVTCL, R&D Altanova, UI Green, and our exhibitor sponsors, ELES, MJC, Phoenix Test Array, and Smiths Interconnect. Please, when you have an opportunity, thank them for sponsoring and making this event possible. And once again, we'd like to thank our premier sponsor, Kohu, the market leader in test interface solutions for the most challenging applications, and ISC, the global #1 total test solution provider. And with that, I will thank you all for joining us today and look forward to seeing you back here tomorrow. So thank you again for joining us and have a good day.
Thank you all.